Hi everyone, my name is Kevin Seville, and today I'm going to be covering a project I did a few months ago. This is Flappy Bird with genetic algorithms integrated into the game to learn how to play the game theoretically better than a human can. So to get started, what is a genetic algorithm? So a genetic algorithm is a search and optimization method inspired by natural evolution. So you have a population of candidate solutions. These are going to be considered your chromosomes. You have a fitness evaluation by a problem-specific objective. You have genetic operators, elitism, selection, crossover, and mutation. And then you iterate towards higher fitness solutions. So when we apply this to Flappy Bird, I'm just going to give an example of playing this manually in user mode. So this is a population of 1. My fitness function is getting the highest score. So to get the highest score, it is just get through as many pipes as you can without dying. So whenever we apply genetic algorithms to this example, it's very simple because the objective is press the space bar, don't hit the pipes. In this example, we're going to have about, I think 50 to 200 of these birds playing. So we're going to change over to the mode that actually integrates genetic algorithms. So this is generation 1. This is just less than a second after starting and pull it from the other window. Our initial population was 100, and right away, we haven't even gone to the first pipe, and about 3/4 of our population has died before even reaching the first pipe. And already on the first generation, we had one where the fitness made it through one pipe. And so we're just going to watch it a little bit, and you're going to see quickly how generation by generation the game learns to play itself. So as we apply the core principles of genetic algorithms to this, we have a population of 100. We have a fitness function that is defined by how far the bird gets before dying. So how many pipes are they getting from before they hit something and die? They either hit pipe, they get to high, they hit the ceiling, or they hit the floor. And then you have genetic operators that define the next generation. So you have elitism, which has the top performing bird has a direct copy as a child. So the parent is identical to that specific offspring. Next, you have selection. So let's say you want the top 50% of the population to become parents and create offspring. So then the lower half, their weights get lost. In that process, you need to cross over their genetics. So in this case, the weights for each instance of the bird. So the properties from those parents combined into the children. So to kind of give an example here, we have bird 1, bird 2. Bird 1, all their DNA is just 1s. Bird 2, all of them are 0s. We have a crossover point. So the first half of the DNA is going to swap over. And so whenever you look at what happens to the child, you have 0, 0, 1, 1. And then for child 2, you have 1, 1, 0, 0. So this is your crossover point. Next, there is a concept called mutation. This is simply mutating one of the elements of the child's DNA. This was originally 0. With mutation, we changed to a 1. So this actually modifies the weights of that specific offspring and may change how it behaves in the next generation. So this is our core genetic algorithm cycle. You start with a random population, you evaluate each individual's fitness. So as we can see, we're already on generation 44, and we have a series of birds that are already doing pretty well in the game just from this session alone. Each generation, the fittest parents, or survival of the fittest. Individuals become parents, have children via crossover mutation. The top performing individual is a direct copy to the child via elitism. And then we repeat the population, or we replace the population and repeat until we have convergence. So mastering the game, essentially. Why use genetic algorithms? So this type of solution to learning a problem is very applicable for complex, non-differentiable search spaces. So to give a very high-level, simplistic description of what I mean by that, let's give an example of you have a giant island where you're trying to find the best treasure chest. There's multiple treasure chests. Some are good, some are bad. One of them's the best. The island is full of various sorts of terrain, like hills, valleys, trapdoors, teleporters, even fog. So you can't see very far. You're just moving a little bit, and you land somewhere totally different each time. In a gradient descent type of solution, you would have an explorer that uses a map and compass that only works if the land is smooth and easy to climb. So essentially they follow small changes in heights, so your gradients to go up and down. However, this island, as we've mentioned, has cliffs and trapdoors. So this is discontinuous, so you have sudden drops or jumps. You have wind and fog, so noisy, hard to measure if you're making progress. You have maze puzzles, so combinatorial, many choices, essentially like solving a Rubik's Cube. So this has the gradient descent solution breakdown because the explorer is essentially going to get stuck or lost. Where you look at genetic algorithms, instead of having just one explorer, genetic algorithms would have essentially a whole team of explorers. So your population, where each one is trying a different spot. They don't need to have a compass or smooth land. They're essentially just finding which treasure chest is better, even if it's far away. So from there, the individuals will keep the better treasure maps. We're going to mix parts of the good maps together or make small random changes. So for the first result, keep the better treasure maps. That's going to be your elitism. Mix parts of the group maps together. That's going to be your crossover. And then make small random changes to the map afterwards. That's your mutation. So over time, the team will just get better and better at finding your treasure, even on unpredictable islands. So it's just, is this better? If so, let's keep it. Next, global search reduces chance of local optimum trap. So to give an example of this, let me go back to our little canvas here. So with a gradient descent problem, you might have a problem like this. I'm going to mark each point, 4, 5, 6, 7. So a gradient descent problem might initially start here at 1, and the objective is to get to the highest point. It might start going up and then come to a local optimum where it thinks it's reached the highest point, but we know here that the global optimum is at 3. It's the highest point. With gradient descent, it might not know that. It thinks if I keep going to 2, I'm going away from the optimum. So we're going to mark this in orange, global in green. So with genetic algorithms, you can avoid that trap of being a local optimum because through your generations where you introduce mutations, even if you get stuck at 1, your local optimum, with mutations, it'll actually force your population away from this local optimum and will have you have a higher chance of reaching that global optimum. Next, parallelizable evaluations speed up processing. So in this case, we had 100 instances of a bird all running at the same time. And for 44 generations, we're in 44th generation, and it seems at this point, the bird's figured out how to play the game. It's doing a pretty good job. It's already hit 239, 240. So we quickly learned how to play the game by having 100 birds play at the same time, have offspring, combining the best traits of parents into the offspring and repeating until we had a perfect solution here. And then next, all we need is a fitness function. We just need to define what's the best fitness here, which in this case is reaching the pipe. So when we apply genetic algorithms to Flappy Bird, the goal is to evolve birds that learn optimal flap timings. So we start with a chromosome, which in this case are our neural net weights, and some rule parameters. We have a population of 50 to 200 birds per generation. In this example, we have 100. I'm actually going to start this over again, just to show that, hey, we can have this learn again. So let's start it over once more. So start from scratch. So population of 100. And then our fitness is a score on how many pipes are the birds getting through before dying. We have selection, where we keep the top scores of parents. And we have crossover mutation, where we mix the weights for the offspring. So our workflow and expected outcome, we simulate all the birds in parallel for one run. We record the scores as fitness values. We apply genetic algorithm operators to create next generation, and then iterate over about 100 generations. However, in the prior run, we got lucky and we had a viable solution after only 44 generations. And then the outcome is the birds discovered near optimal flap timing, often beating human play, which, as I was describing genetic algorithms and how they applied to Flappy Bird, it achieved that in this video, where by generation 44, we had a bird that was exceeding a score of 240. So I'm just going to let this sit for a bit and see how far it gets. Okay, so it looks like we got pretty lucky on this generation as well. We're only on the 19th generation, and we already have 3 birds alive, 2 now, where it's getting pretty far in the game. So what's probably going to happen is we're going to end up with birds exceeding the highest score below generation 44. So this starting population ends up performing better just by the random weights that they were started with, mutations that affect their weights, how they perform, and also crossover. So from there, I'm going to end this simulation here, and I'm going to load up some pre-trained weights where I had this running for about a week. It kind of got redundant to a point because the last generation lasted about 5 days and the birds didn't die. So I ended up just having to cut the game off and not actually save those weights because the generation never ended. What I eventually implemented, however, was a mechanism that would auto-save the weights in between the generations, because at that point, the birds are so good at the game, you would have to wait an extended period of time before you get a new generation. So just having a checkpoint within that generation lets you at least copy the current weights and reuse them. So with this checkpoint, we have those weights applied to just 20% of the population. So we have 20 birds that are performing virtually identically, and it's perfected the game. It knows the optimum flap patterns, as we begin the game. So that pretty much covers this project here. There's going to be another showcase in hopefully a few weeks regarding flow game, using A-star heuristic and other techniques to solve the game space, going from squares to the hex, and also incorporating other obstacles like bridges and walls. So I'm looking forward to that. I'm going to be including a link to this repo so others can take a look at it, see how it was written, and then ask any questions in the comments. So it's my first video in quite a while, so thanks for watching, and you all have a good day.